Yes. Hi, fellow absent people. Um, we are now recording. It's approximately 5 after 5, so we've been going now for almost 15 minutes of me babbling and saying basically nothing. But I was just explaining that tomorrow night, as in Friday, the 17th
Yes.
of September, there's an outstanding opportunity, if the weather cooperates, to see the International Space Station fly over as it travels 17,400 miles an hour in orbit about 200 miles above the Earth. And to make a long story short, since we don't have forever, at precisely 8:13 tomorrow night, if the sky was clear and you were to look in the southwest sky, and right at the moment I'm not going to try to figure out where southwest is. I think southwest is that way, I think maybe. You look in the southwestern sky, and you look about 10 degrees above the horizon, in other words, basically behind the trees, behind the buildings. And you would watch in that direction. Once it pops into view at 8:13, it will move across the sky, and it's going to reach a maximum elevation. This is very unusual. It'll reach a maximum elevation of 86 degrees, which means almost directly overhead. And it's going to be visible for a huge length of time. It's going to be visible for a whopping 6 minutes as it goes across the sky. Takes 6 minutes to get all the way across, and it will disappear in the northeast horizon. There's much more that could be said about it. It's pretty cool stuff, but you'll recognize it because it kind of looks like a star, but it's moving. It will not be flashing. It doesn't have flashing lights. It's not giving off any of its own light at all. Well, a little bit of light coming out the windows, but you can't see that from 200 miles away. All you can see is the sunlight reflecting off of it. And so it kind of looks like a star. You recognize as being a space shuttle no, not anymore. You'll recognize it as being a space station because it will pop into view in the right place at the right time, and it will be moving in the correct direction. And you say, that must be it. Yes, like a star, just slowly moving across the sky. No flashing lights, just a steady light. And it's kind of cool to look at that thing and say, I'm looking at an object that right now is about 200 miles away. It's in orbit around the Earth, and it's moving at 17,400 miles an hour, and it's got people on there, and I'm looking at it going over my head. It's so cool. So if that kind of thing fascinates you as it fascinates me, and if the sky is clear, try to remember tomorrow night, set your alarm, 8:13. It starts off so low on the horizon you might not see it until like 8:14 or something. But 8:13, 8:14 in the southwestern sky, and expect it to pass right over your head. So it's neat to see. What's even neater than that, when another space vehicle, like the SpaceX space vehicles, Elon Musk's vehicles, when they dock with it, you can actually see the two objects, one trailing after the other, as they go across the sky with the crew capsule chasing the space station as they're trying to dock. I've never seen that, but it's cool if you ever do see it. Now, before I forget, I want to pass out the tests. For the folks who are absent tonight, I will most likely scan these and send them to you by email. But everybody else, you get your own personal copy. Now, as far as tests, for those who are not familiar with the policies, and I have at least one policy of my own, you are, of course, to open these in the presence of a parent when you're ready to take the test. The parent is to supervise the taking of the test, being there in the room with you. No computers handy, no books open, no notes, no nothing. Just you and the test, and sometimes, if necessary, a calculator, but on this test, you don't need a calculator. When you're done, I would like the parent to sign the test, but more importantly, they are to put it into a new envelope, seal the envelope, and I've had some problems in the past with, I don't like it when I have reason to doubt the integrity of a student, even if they're totally innocent. If I see things that causes me to wonder, I really don't like that. I've found that I've seen some weird things. Don't do this. And I've seen this happen way too many times. A parent is busy. Says, oh, I don't have time to watch you take the test. Here, I'll sign the envelope in advance, and then you can take the test, put it in there, and seal it up, and no one will ever know. I know. I can tell when an envelope has been pre-signed. Don't go there. Don't have your parents pre-sign the envelope. That's a violation of chieftain policy, and it's just not right. So you finish the test, put it in here, parent seals it up, signs, and puts a piece of tape across the seal. Okay, put a piece of tape across the seal, and then have the parent sign on the tape. Not because I don't trust you, but because if they do that, if they put tape across there and sign across the tape, then there's no way I'm going to doubt the integrity of the test-taking experience. It just lets me know that I don't have to worry about it, that as far as I can figure out, everything is okay. All right. Enough said about that. I gotta put this over here so I don't forget to mail these. Yes?
So you want this in a different envelope?
Well, I mean, I guess you could reuse this one, but by the time you get this opened, it's going to be a bit of a mess. A new envelope is better.
So if I do get it open and it's nice, can I still use it maybe? Cool.
What I've had some students do in the past is their parents like to save all of the junk mail. You know, all this junk mail that comes with envelopes inside it. They save all those envelopes that get sent to them, and they use those. So you see, Publishers Clearinghouse, you know, and I stick it in there and all this stuff. So, I'm not real picky about what kind of envelope it comes back in. I've had some folks who fold it up into this little tiny thing and put it in a little tiny, tiny envelope. if you must. All right. Let's pray and finally get into checking the assignment and making sure you're as ready as possible for the test. Let's pray. God, thank you for your love for us, for Jesus our Savior, for the laws of physics that you invented and how cool it all is that we get to study it together. God, most of all, again and again and again, we thank you for our Savior. We thank you for what you did for us on that cross 2,000 years ago. The difference you make in our lives today. The promise of eternal life to everybody in this room who believes. Thank you. So keep us awake tonight and just enable us to focus and think clearly, including me. In Jesus' name, amen. And before, there was one other thing I wanted to do before. I didn't show you this last week. Now, folks, how shall I, let's try this. I'm going to move you. Okay, will that do? Yeah, that's not bad. It's not a real close-up view, and no, I'm not going to try to zoom in because I don't have time. I saw this in a science teacher's supply catalog. Yes, there are such things as science teacher supply catalogs. Oh, I wish I had a $1,000 gift card for one of those catalogs. There's so much cool stuff in there. But I actually saw this in the catalog. They were selling a block of wood and 18 nails for like $8. And I'm looking at it thinking, I don't need to pay them $8 for that. So I went to my basement, I got a block of wood, drilled a little hole in it, got 18 nails from the Home Depot, and voila, I saved myself a boatload of money. Well, a small boatload, small canoe load, I don't know. But here's the deal. I am going to, with one nail in the block, as you at home can see there, one nail in the block, I'm going to stack the remainder of these nails, and I don't know if I actually have 18 of them here anymore, but I'm going to stack them all on top of that one nail. No, you're not. Yes, I am. Watch this. First nail on top. Maybe if I do two at once, I'm going to get all 18 of these nails on here. He's not going to be able to do it. Yes, he is going to be able to do it. I have nearly infinite patience. Let's try this way. I will take, let's stand over here closer. I will take two nails. And I'm not much good with chopsticks, but I'm going to attempt to hold these two nails parallel to each other, like this, like this. And now I'm going to insert a nail there, and another one here. Ah, yes. And another one here. and one fly there, here. Now normally, before I finish this process, I end up dropping them all. Because, like I said, I'm not real good with chopsticks. And there. My daughter is very good with chopsticks. Too bad she's not here right now. There we go. Yeah, my daughter is not Asian. She just is very good with chopsticks. Okay, and there. And am I gonna, oops, dropped one. There. And, instead of taking time to do all of these, perhaps I'll just stop there. Although I'm tempted to keep going. Oh, a couple more. It's going so well. There. And there. Oops, lost one. That's two I've lost now. I'm going to stop there before I get in trouble. I now take this assembly, this little weird assembly of nails, and I am now balancing all of those nails on the one. Ta-da! It can be done. Thank you, thank you, thank you, thank you. Now, there's a reason why I do this, because what I now need is a piece of paper. This should do nicely. And I wasn't thinking, I should have put the paper under this before I stacked them. Okay, I'm going to try to very carefully lift this contraption. And I'm going to turn it sideways like this. You might be able to guess what I'm going to attempt to do. Now this works approximately, maybe 30% of the time. So I'm not going to be at all surprised if it fails miserably. But what am I going to do?
Pull the paper?
I'm going to pull the paper out from under the nails that are delicately balanced on top of the one nail. Okay. Like I said, it works about 30% of the time. But if you are willing to believe it, it does work 30% of the time. I think the problem is these tables are not real slick. So there was a little bit too much of what?
Friction.
A little bit too much friction there. But if it had worked, that would be a demonstration of what property?
Inertia?
Inertia. Inertia of what? Inertia of the paper, the nails, the table. What is it that when I pulled the paper out did not want to move if they had worked properly? The nails did not want to move. So had it worked properly, I yank the paper out and the nails stay where they are because the nails have inertia. I wish it had worked. And no, I'm not going to try it again. Did anyone know where the other nails went? I mean, I'll tell them. Oh, thank you. Okay. Did I pick them up or did you?
No, you picked
I picked them up. Good grief, I'm getting old. Okay. Gee whiz. Sometimes I wonder, maybe I should retire. My brain is just not functioning very well. No, not retiring. Never. Now, let's get into the problems here. Now, the official review questions on the left side of the page, we should be able to go through fairly quickly. Number 6. What did Galileo discover about moving bodies and force in his experiments with inclined planes? And he did all stuff with balls rolling down inclined planes, and he concluded that, thank you, I forgot to fix that. He concluded that an object, once it gets moving, wants to
Keep moving.
continue moving, yes. Now, it says here, what did he decide about moving objects and force? Well, that in the absence of a force, it's going to keep moving. If there is a force, it'll change, but otherwise, without a force, it's going to keep moving. In other words, he discovered inertia. So it was not, as we said before, it was not Newton who came up with the idea of inertia. It was actually Galileo who came up with the idea of inertia. Number 7. By the way, this is one of the reasons why I do not grade these on accuracy, because there are about 97.5 different ways you could express the answer to that, some of which might be on the right track, some not on the right track. So please take notes and make changes, make corrections. If you say, oh, I see now, write yourself a note. I'm not collecting these. I almost never will. Number 7. What does it mean to say that a moving object has inertia? Well, that's a little hard to put into words. To say that it has inertia simply means that its nature is to hello? Keep going if it's already moving, or to sit still if it's already sitting still. That's what inertia is all about. An object at rest will remain at rest. An object in motion will remain in uniform rectilinear, fancy terminology for uniform straight line, constant speed straight line motion. So that's what inertia is. Give an example. Well, we can give a zillion examples. Ball rolling across the floor. Keeps on going until it hits something. That's inertia. Number 8. I like number 8. Number 8 is one of those kind of things that sort of plays with your mind. Number 8 is asking, is inertia the reason for moving objects maintaining motion, or the name given to this property? Well, clearly it is the name given to the property. You can't say that it's moving in a straight line at a constant speed because of inertia. It's better to say, well, that's its nature, and we call it inertia. Is inertia a force? No. Inertia is not a force that keeps things moving. Inertia is simply the name we have given to the fact that an object's nature is to continue in its state of motion, whatever that may be. Of course, contrary to what Aristotle taught. Aristotle said, of course, that it's only going to move as long as there's a force. And if the force stops, the movement stops. That's what Aristotle said. Aristotle's wrong. By the way, I don't think we mentioned, did we talk about shooting arrows last week? No. Okay, we ran out of time. It's something like this. Evidently, there was a question sort of like this that was answered by Aristotle. So I can just imagine how this went over. We've got Aristotle sitting on his stool. I don't have a stool here. Aristotle, I always picture him sitting on a stool, with his robe and whatever he wears, I don't know. And his students sitting on the floor at his feet, probably little kids. And he's teaching them about the nature of matter. And some little kid says, "Mr. Aristotle?" "Yes, my son." Or my daughter, whatever you are. Oh, that brings to mind. Sorry, getting political here. We'll let him be. "My son?" "Yes, my son."
My daddy was out hunting deer the other day.
"Yes."
And I was watching him shoot arrows at the deer. And I noticed that, just like you said, while the string was pushing the arrow was moving. But Mr. Aristotle,
"Yes."
When the string stopped pushing the arrow and the arrow left the bow, according to what you have taught us, the arrow should just stop moving. But it doesn't. It keeps on going.
"My son, you raise a very good question. Allow me to answer that tomorrow. I must think about this." Oh, I'm off camera. Hi. Okay. I'm over here thinking, okay? On my stool. Oh, that's better. Thank bless your heart. Thank you. That's good. That's perfect. Beautiful. Okay. So he goes home and he thinks about it for a while, He comes up with this answer, believe it or not. "My son, I have an answer to your question."
Oh, bless you. We knew you would have an answer.
"Yes, here's my answer. As the arrow goes through the air has to part ways and go down the shaft of the arrow. But as it does so, it leaves a partial vacuum behind. You can't have a vacuum. The air comes in behind the arrow and fills the vacuum and pushes the arrow from behind."
That's so brilliant. Thank you, Mr. Aristotle. Now we understand. The arrow is being constantly pushed by the air from behind.
"Yes, my son." What nonsense. But that's what he taught. He had it all figured out. just a little tiny itty bitty bit of experimenting. And Aristotle could easily have been disproved. But everybody was afraid to even try. Well, anyhow, moving on. Number 9, Isaac Newton's first law of motion. Hey, we've already been through it. An object at rest will remain at rest. An object in motion will remain in straight line, uniform speed motion until acted on by an outside force. You can read it for yourself someplace in the book. Newton's first law. An elaboration on Galileo's discoveries. Remember that Newton was born the same year that Galileo died. So Newton continued Galileo's teachings. Number 10. What is the net force? Net force. That's when you add up all the forces and see what you're left with. What is the net force on a cart that is pulled to the right with 100 pounds and to the left with 30 pounds? Net force must be 70 pounds to the right. Okay, simple enough. That 30 cancels out 30 of the 100, leaving you with 70 that way. The cart will respond as if there were a single force of 70 pounds to the right. Moving on. Number 11. Why do we say that force is a vector quantity? Because force has both magnitude, size, and direction. That's what makes it a vector. It has magnitude and direction, such as 100 pounds to the right or 30 to the left. It has both magnitude and direction. That makes it a vector. That's all there is to what a vector is. Number 12. Is it possible, can force be expressed in units of pounds and also in units of newtons?
Yes.
Yeah. Let's make a little chart here to clarify. Hopefully, let's see. I can see from here to about here. Okay, so I've got this area to work on that folks at home can see me. Okay, we've got these two things going here. We've got mass and we've got force. By the way, very important to recognize, and I find that some folks get a little confused about this, weight is a force. I'll write that word on here. Weight happens to be a force. Okay, so we've got mass and force. Then on this side I'm going to write, now I think the proper terminology is imperial, but imperial. I prefer to just call it English, okay? We got the old English units, and we got the metric units. Do you realize, in case I didn't mention it last week, and in case you didn't know it, we are the last country on the planet that still uses the stupid English system. I mean, who came up with 12 inches in a foot? Why not 10? I got 10 fingers. 12 inches in a foot. 3 feet in a yard. Where did that come from? 5,280 feet in a mile. Are they trying to torture us with these numbers? How many square feet are in an acre? I have no idea. Never have known. I've seen it, but I'm not going to memorize that. Ounces in a pound. Different than ounces in a cup. Those are totally different. Oh, what a mess the system is. In the metric system, basically, you have to know one number. It is 10. In the metric system, everything is based on tens. Tens and powers of tens. 10, 100, 1,000. It's so easy. That's why the rest of the world has converted from the imperial system to the metric system, because it is so much better. In our country, architects, engineers, and common folk still use the English system. Scientists use the metric system. Why would scientists use the metric system? So that they can, communicate with
Other scientists?
the rest of the world. Yes. Scientists have switched to the metric system. But folks who just work here, folks building buildings in America, folks building bridges in the United States, folks doing highway engineering, whatever, they all use the English system still. But units of force. In English, in the imperial system, force is measured in pounds. We're all familiar with that. Of course, the abbreviation of pounds is LB. Where did that come from? I looked it up a couple years ago because I didn't know. It's Latin. It makes sense when you see it. It's Latin for some word that represents pounds. I don't remember what the Latin word was, but it does actually make sense in Latin. LB for pounds. In the metric system, force is measured in
Net force?
newtons, yeah, in honor of
Newton.
a guy named Galileo. No, in honor of a guy named Newton. Newtons. And they're abbreviated just with a capital N. All right. In the metric system, mass is measured in
Kilos?
yes, kilograms or grams. What's a kilogram? A kilogram is simply kilo means 1,000. It's 1,000 grams. But most often we use kilograms. So in the metric system, our main unit of mass is the kilogram, abbreviated as kg. I'm not going to spell it out. Not very many people know the units of mass in the English system. Very few people know it. I don't know of anybody who uses it for anything. But there is a unit of mass in the English system. And yes! I'm not sure I've ever heard anyone who just knew it right off the bat like that. Yeah, it's the slug. I don't remember how they compare. I believe a slug is actually pretty heavy. Much heavier than a kilogram, I believe, if I'm not mistaken. Yeah, the slug. Which kind of makes sense when you think about it. We're not talking about slimy creatures. We're talking about, I hate slugs. We're talking about things like you refer to a bullet as a slug. You can refer to those things that you, those little flat discs that you file off just right, and then you can use it to get free drinks out of the soda machine. They refer to that as a slug. How do you know that, Mr. Spear? Anyway, yeah, so the unit of mass in the English system is slug. Now please understand, mass and force, kilograms and newtons, slugs and pounds. Mass and force are totally different things. Totally different things. We'll have more to say about that later. I may have mentioned it some last week, but it'll become more important as time goes on. They are different things. For instance, real quick, here it is. This 1 kilogram mass. This is 1 kilogram of mass. It has a weight of about 10 newtons. So 1 kilogram weighs about 10 newtons. What it is, how many slugs is that? I have no idea. But it weighs about 2.2 pounds. So 10 newtons is about 2.2 pounds. 1 kilogram on Earth weighs about 10 newtons, about 2.2 pounds. All right, now, all of that is just kind of little background stuff. So can force be expressed in units of pounds and also in units of newtons? Most definitely. Force, pounds, newtons, yes. Number 13. Depending on how old your book is, there was the original printing of the 9th edition, and then there was at least one subsequent printing of the 9th edition. The older 9th editions have an error in number 13. The newer printings of the 9th edition do not have that error. He fixed it. He says in 13, in my version of the book, what is the tension in a rope that is pulled with 100 newtons to the right and 30 newtons to the left? We'll see in a later chapter in more detail why that is just plain impossible. You can't have different tensions on each side of a rope. A rope can only have one tension. The question makes no sense. So in subsequent printings, he changed it. And so, bummer, yeah, we can't talk about tension being different, so we'll talk about force on an object being different. So he changed it to something like, what is the net force on an object? This pulls 100 newtons to the right and 30 newtons to the left. And it never occurred to the person who made the correction, never occurred to them that they were simply writing an exact copy of number 10. They should have changed the numbers at least. But yeah, 10 and 13 but basically turned into the same question. So the answer is once again 70 to the right this time. Oh, was it to the left last time? Oh, he changed it.
Wait, it was.
No, they were both right. Yeah, that's right. It was right before also. Yeah, 70 to the right. I'm curious. How many of you have the correct version where it talks about force on an object? Anyone have the one that says tension? Have we got a tension person, a couple tension people? Okay. Interesting. Number 14. What's the net force on a bag pulled down by gravity with 18 newtons and pulled upward by rope with 18 newtons? Force of weight down 18, rope pulling up with 18, down and up, opposite directions, equal magnitude. What happens? Net force is 0. We're talking equilibrium. We're talking that thing's not going to go anywhere. Or if it's already moving, it's going to keep on moving. Number 15. What does it mean to say that something is in mechanical equilibrium? Well, it simply means that the sum of the forces must be 0. Does that mean it has to be sitting still? No. It could be moving in a straight line at a constant speed, such as, where did I put my bag? There it is. Such as the sandbag. If it's sitting still, the bag is in equilibrium. Sum of the forces is 0. How many forces on the bag right now? At least 2. It's weight down, and what do you call that upward force for my fingers?
Surface force?
Support force. So it does start with S. Support force up, support force equal to weight downward, sum of the forces is 0. If I move it across the room in a straight line at a constant speed, like it or not, as we emphasized last week, there are still only 2 forces. There's support force up, and there's weight down. No horizontal force is required to keep it moving. In fact, what keeps it moving horizontally? Inertia. Nothing. That's its nature. So the sum of the forces is still 0. So how can you tell when something is in equilibrium? Either it is sitting still, or it's moving in a straight line at a constant speed. Either way, you know it's in equilibrium. Either way, you know that the sum of the forces must be 0. Moving on. Number 16. State the equilibrium rule in symbolic notation. Oh, that's easy. In symbolic notation, we simply write, after clearing some space on the board, we simply write sigma, the sum of the forces, is 0. You will see that on the test, by the way, so make sure you recognize it as being the symbolic way of saying that the sum of the forces is 0. That's the equilibrium rule. The equilibrium rule. 17. Consider a book that weighs 15 newtons at rest on a flat table, such as this one. Is that 15 newtons? I have no idea. We'll pretend. 15 Newton book at rest on a flat table. How many newtons of support force does the table provide? The table must be pushing up with 15 newtons. We know that's true because the book's not going anywhere. The forces have to add up to 0. So if it's got 15 down, there must be 15 up. The table is pushing back with 15 newtons of force. Sum of the forces is 0. What is the net force on the book in this case? 0. Net force is 0. Number 18. When you stand at rest on a bathroom scale. When you stand at rest on a bathroom scale, how does your weight compare with the support force by the scale? Well, rather obviously, they're equal. Equal but opposite. Yes, they are equal. Otherwise, you would be going someplace. It'd be kind of interesting if you step on a scale and it pushes you to the ceiling. But that does not happen. They add up to 0. Number 19. We got a bowling ball at rest. It's in equilibrium. Okay, yes, we know. Is the ball in equilibrium when it moves at constant speed in a straight line path? If I grab the bowling ball, very small bowling ball, and I roll it across the table at a constant speed in a straight line path, doing it here so the folks at home can see it. There it goes. They saw it go by. Is it in equilibrium? Yes. If it's going in a straight line at a constant speed, yes, it's in equilibrium even if it's moving. Okay. Make sure you're clear on that. Number 20. What is the test for whether or not a moving object is in equilibrium. Oh, well, the test is simple. Is it moving in a straight line at a constant speed? That's the test. Oh, I was looking for something really complicated. No, it's that simple. It's that simple. And 21. If you push on a crate with a force of 10 newtons and it slides at constant velocity, how much friction must there be? Well, if I push with, what was it, 10 newtons?
100.
100, thank you. 100 newtons of force, but it moves at a constant speed. There must be a force in the other direction of 100 also. So the forces add up to? Zero. What's the source of that other force? The only thing possible is, and you can hear it, friction. So I've got 100 newtons of force that way. I've got 100 newtons of friction force that way. The two add up to zero. And that is why it moves at a constant speed, which is contrary to common sense. I know that is kind of troubling to the human mind. We say, well, it's moving because you're pushing it. Okay, yeah, true. But we have to understand, and it's critical for the future, that what's keeping it moving is actually inertia, because my force is being canceled out by friction's force. The sum of the two forces actually is zero. It is in equilibrium, which is why it moves in a straight line at a constant speed. What would happen if there was more friction? Then I can provide force that way. It would slow down and stop. Or if I push harder than friction is able to combat, then it would speed up. Which helps to explain a lot if you think about it. But as long as the friction and my force are equal, it will move in a straight line at a constant speed due to inertia. Now, I didn't have you do 23 or 24, did I?
No.
Okay, we move on then to exercise number 5 on the second page, actually. Okay, the other number 5. Was it Galileo or Newton who first came up with the concept of inertia?
Galileo.
Galileo, contrary to what a lot of folks might think, it is indeed, yes, Galileo, good. Number 6. Now, here's a point where some folks, depending on your theological view, some Christians believe that the earth, the universe, is extraordinarily old in terms of billions of years. Other Christians, spirit-filled believers, believe that the earth is only about 10,000 years old. Both sides, perfectly good, born-again believers in the Lord Jesus Christ, so we don't condemn either side, but just understand there are some believers who think it's very old, and there are some believers who think it's very young. It's the great debate. Kind of fun to talk about, but it's not worth getting upset about. So when Paul Hewitt talks about something moving through space for billions of years, don't be offended by that. Just if you think the Earth is the universe is young, just say, "Oh, Paul Hewitt, silly man." If you think the universe is very old, then say, "Yeah, right on, Paul Hewitt." So yeah, don't worry about it. Remember, though, Paul Hewitt is not a believer, so don't be offended by things that come up like number. Where are we? Number 7. 6. Thank you. So number 6. Asteroids have been moving through space for billions of years, or maybe only 10,000 years. What keeps them moving? Nothing. Yeah, I like that answer.
Inertia.
Nothing.
Inertia.
What answer do you think Paul Hewitt was looking for?
Inertia.
Inertia. Yeah. It's funny how he emphasizes that inertia does not keep things moving, but then he uses that same language. Yeah, we tend to be a little inconsistent sometimes. Me too. We recognize that inertia is not something that keeps things moving. It's just the name we give to the fact that that's what things want to do. However, I and Paul Hewitt will often talk about how inertia keeps things moving. We'll forgive ourselves for that. So yeah, he's looking for the word inertia. Let's see, number 9. Your friend says that inertia is a force that keeps things in their place, whether at rest or in motion. Do you agree? Is inertia a force that keeps things in their place, whether at rest or in motion? No, inertia is not a force. If we believe inertia is a force, that's going to cause us all kinds of confusion because it doesn't work. I'm not going to try to go through why it would be confusing, but no, it doesn't work. Moving on. Number 11. Consider a ball at rest in the middle of a toy wagon. Here's my toy wagon in view of the folks at home. And we've got a ball in the center of the wagon right there. Now this demonstration is not perfect because it's not a frictionless surface and the ball is going to be made to roll, which kind of ruins this. But if we can pretend for a moment that the ball is actually on a frictionless surface, when I move the cart towards, say, your left, my right, like this, the ball which wants to roll off the cart, and that just happens so fast it's hard to really visualize, but you understand. The ball tends to go toward the rear of the cart, right? As I do this, the ball goes toward the rear of the cart. Why? Because the ball wants to stay where it was, and that is caused by inertia. Now, of course, this bouncy ball is hard to see because as soon as it hits the back, it bounces the other way, but you get the idea. The cart moves, the ball wants to stay behind. Just like the nails balanced on the nail, on the other nail, they want to stay where they are even though I'm moving the paper out. Same concept, same thing exactly. Trying to move faster here because we spent so much time babbling at the beginning that I am running behind now. Number 14. Okay, why do you lurch forward in a bus that suddenly slows down? As you're going along in this bus, one of those EYRE, it's pronounced air, and their slogan, travel on air. That's so clever. You're on one of these air tour buses. You know how smooth those things are? You don't feel like you're moving at all, you know? You're traveling along 60 miles an hour. And I don't know if I used this illustration last time or not, but either way, you're going along. And it happens. Montgomery County, it has to happen. A deer jumps out in front of the bus. And the bus driver says, "Oh no, not another deer!" And he slams on the brakes. As the bus suddenly slows down, you are lurched forward. Or are you really? What's happening? It's not that you are being pushed forward. It's really that the bus is suddenly slowing down while your body that was moving at 60 miles an hour forward wants to continue moving forward at 60 miles an hour due to inertia. So you're not really being pushed forward. It would be more accurate to say that the bus is being pushed backwards. You are simply trying to continue at 60 miles an hour while the bus is slowing down around you. And from your point of view, it feels like you're being lurched forward. That's the funny thing. You're really not. You're not being lurched forward. You're just trying to go in a straight line at a constant speed. And the bus is saying, "Nah, let's not do that. We're going to slow down." "But I really want to keep moving forward at 60 miles an hour." Sorry. And so you feel like you're being pushed forward in the bus. What was that? That was number. Oh, how about if the bus picks up speed? We're going down 270 again, 60 miles an hour. That same deer, same one, jumps out in front of the bus again. This time the bus driver is just totally fed up. Says, "You've had it, dude." Yeah. So he hits the gas. Okay. When he speeds up, you feel like you're being lurched backward. Why? Because your body wants to continue moving at 60 while the bus around you is picking up speed, 60, 70, 80, 90, 100. And you're being, in a sense, left behind because you're only doing 60. So the result is you feel like you're being pressed into the seat. As your body wants to continue at a constant speed while the bus is picking up speed, you feel like you're being pushed backwards. You're not being pushed backwards. Actually, it would be more accurate to say what? Are you being pushed backwards? No. The bus is actually pushing you forward against your will. Your will is to continue at 60. And the bus is saying, "No, we're going to push you faster than that." You're actually being pushed forward. It feels to you like you're being pushed backwards, but you're not. It's all about inertia. Number 16. Oh, I'm glad he told us this in the first sentence. We didn't know this. Push a cart and it moves. Thank you. Okay, hopefully there's more to the question than that. When you stop pushing it, it comes to rest. Let's try this. Push, it moves. Stop pushing, it comes to rest. Ah, true. Aristotle is evidently correct. Does this violate Newton's law of inertia? Well, obviously, yes. That's what Aristotle thought it certainly violated. Newton's a nitwit. Is what Aristotle would have said. But no, we know that the reason it comes to rest is because of friction. Aristotle didn't understand friction at all. Didn't understand it. So no, it doesn't violate anything. Friction takes over. Friction provides a rearward force. Remember, friction always opposes motion. If the object's going that way, friction will be the other way. And that friction will cause it to slow down and stop once I stop pushing. So no, there's no violation there. Number 18. Consider a pair of forces. One having a magnitude of 20 newtons and the other 12. Oh, interesting. 20 and 12. Now here's an interesting thing about vectors. If I have a 20 Newton force to the right, I can represent that with an arrow of length 20. 20 what? I don't know, I don't care. 20 inches, 20 centimeters, doesn't matter. 20 units. And if I have another vector, another force with only 12 newtons, it would be about, maybe about that long. That might represent 12 newtons. 20 newtons, 12 newtons. Cool thing about vectors that if I had my smartboard here, I could demonstrate this by picking up that arrow and moving it around. I can put that vector any place I want, and it's still the same vector, as long as I don't change its, what does a vector have? Direction and magnitude. Whether I put it here, or up here, or down there, as long as I don't change its magnitude or direction, it's still the same vector. It doesn't matter where I put it. Now, if I've got these two vectors, and I don't know which direction they're pointing, what is the largest possible force I can get out of those two combined? If they're both pointing on an object that's in the same direction, the maximum force would be 32 newtons. What if, on the other hand, am I still in view here? Yes. What if the 12 Newton force were pointing the other direction? So they're opposing each other exactly. Now, what's the minimum possible force with those two? 8 newtons. So your maximum would be 32 newtons with those two. The minimum possible force would be 8 newtons if they were acting against each other. And anything else, we're not going to. Well, later in the book, a little bit we will. But you would need some trigonometry or some Pythagorean theorem to figure out what would happen if they were in weird directions like that. But if they're like that, then there are things we could do to figure out what would the force be. But it'll be someplace between the two extremes. So minimum possible would be 8, maximum possible would be 32. Don't worry about what happens in between, that comes later. Number 19. Is it possible to have something in mechanical equilibrium if only one force is acting on it? No. Because if you've got just one force, well, in order to be in mechanical equilibrium, you've got to have something balancing it out. And if there's only one force, what's going to balance it out? Nothing. So you can't have mechanical equilibrium with just one force. Hey, here's a quick example. We haven't addressed this much yet. We'll address it in a later chapter in more detail. But if I drop the bag, right now, how many forces on this bag? At least 2. Weight down, support force up. If I release it, there's no more what? support force. Therefore, there's only one remaining force, ignoring air friction, okay? There's only one remaining force, which is its weight. Because there's only one force remaining, it cannot be in mechanical equilibrium. If it's not in mechanical equilibrium, it cannot be moving at a constant speed. So guess what it's doing? There's an A word we have not addressed yet.
Accelerating?
It's accelerating. It'll be going faster and faster and faster because the sum of the forces is not zero. So when an object is in what we call free fall, it's speeding up as it falls. That, again, is a topic for a later chapter. In fact, I think we'll get to it in chapter 3, which is coming up next. All right, continuing on. Number 21. Now, don't overthink things. I've had lots of folks who have a tendency to think too hard. But we have to think hard. Don't think too hard. When he talks about a hockey puck on ice, okay, let's think too hard for a moment. Does a hockey puck on ice have any friction at all? Yeah. There is friction between the puck and the ice. There's also air friction. But anytime I or Paul Hewitt talk about a hockey puck on ice, that's our way of saying, let's pretend for a moment that there is absolutely no friction. Okay, don't overthink it. Hockey puck on ice, okay, we're talking no friction. But that's not realistic. That's all right. Just pretend, okay? Hockey puck on ice means no friction. Other things that might mean no friction. Well, sometimes on the test, I'll give you a question and say, ignore friction. But we can't ignore friction. Ignore friction. But, no, just pretend there's no friction. Okay. Don't overthink it. So, back to number 21. A hockey puck slides across the ice at constant speed, but it can't, no, pretend there's no friction. It really is moving at constant speed, we'll say. Is it in equilibrium? Well, if it's going in a straight line at a constant speed, that's the test. So yes, it has to be in equilibrium. But what about the friction? Don't overthink it. No friction. But, no, relax. Breathe deeply. Number 22. Why not? Well, we know why. Okay. 22. The sketch shows a painting staging in mechanical equilibrium. In other words, we're assuming it ain't moving. Or if it is moving, it's moving in a straight line at a constant speed. I would assume it's not moving. The person in the middle weighs 250 newtons. That's kind of funny. I don't know what... I really do not know if Paul Hewitt writes these questions or if some assistant, maybe one of his students, one of his college students writes these questions. I don't know. But I always found it kind of humorous because if you've got a person, that person should not be standing on that staging. Do you know why? Because if he weighs only 250 newtons, that translates to about 56 pounds. We're talking little kid playing around on that staging. No, that 56-pound little kid should not be on that staging. I don't know why he said 250 newtons. I have a weight of about 700 newtons. So he could have said 600, 700, 1,000. That'd be realistic. 250 newtons? What was he thinking? I don't know. But, yeah, we got this little midget maybe. Maybe he's a midget. He might be a full-grown midget, okay? But so we'll ignore all those little details. We got a person exactly in the middle, and he only weighs 250 newtons, little guy. And the tensions in each rope are 200. So we've got what? We've got... And by the way, it is kind of nice to know, just for reference, so you know how to think about these things, that my weight is about 700 newtons. So when someone says, oh, how much do you weigh? You say, well, my teacher weighs 700 newtons. I think that mean I probably weigh about 300, because he's big. Yeah. Anyway, just kind of gives you a reference point, 700 newtons here. Now, we've got the staging. It's a flat board here, being held by these ropes. And in the middle of the ropes, we have these scales. I think we looked at examples of this last week, I think. And they're measuring the weight scales just like this spring scale here. Same deal. We have the dude standing here, little tiny dude, who weighs. Go home to your mother. He weighs only 250 newtons. And the readings in the scales, this one says 200 newtons upward. And this one says 200 newtons upward. That makes sense because he's in the middle. So we've got 400 up. We've only got 250 down. But wait a minute. The staging is not going anywhere. It's in equilibrium. Therefore, what does that imply about the weight of the staging itself? It must be 150. How did they get that? Well, we've got a total of 400 up. We must have 400 down for the two to cancel out. The dude only weighs 250, so we're missing 150. So the staging itself must weigh 150 so that the ups equal the downs. That's all there is to it, and you will find questions like that on the test. I think there are 3 of them like that, where I'll ask staging questions, and all you have to do is make sure that the ups equal the downs. That's all. Fairly simple, right? Right. Number 23. A different staging that weighs 300 newtons, ooh, very heavy board. A different staging that weighs 300 newtons supports 2 painters, one 250 newtons and the other 300. The reading in the left scale is 400. What's the reading in the right scale? Again, you just have to make sure that the ups equal the downs. And he gives us a diagram. How nice of him. All the downs added to what? 6. The downs added to 850. The up, we've got 400. What's missing on the other side?
450.
450. Because the ups have to equal the downs. So the other rope must have 450 newtons of tension in it. The other scale must read 450. All right, now, moving on to number 25. Ah, yes, Harry the Painter. I love this. By the way, it just occurred to me, we're almost done, and I've been moving too fast. I need to slow down some. Harry the Painter. This is Harry. Meet Harry. Harry is even smaller than the dude on the staging earlier, because Harry only has a weight of 10 measly newtons here. Maybe Harry is a hamster or something. But he's on this thing called a bosun's chair. I'd never heard of a bosun's chair before, but remember, Paul Hewitt was once upon a time, in a previous lifetime, was a professional painter, so he knows these things. So he's sitting on this thing called a bosun's chair. What in the world is a bosun's chair? He sits on it. It's got a rope going over a pulley that comes back down, and he attaches it to the chair. It's got 2 ropes across a pulley, both attached to the chair. If he wants to go up, he grabs one of the ropes and pulls. And as he pulls on that rope, it pulls him up. And then he attaches it to the chair again. He wants to go down, he unties it and does this, and the chair goes down, he ties it back to his chair again. Now, this particular rope, we're told here, let's see, the rope is rated to be able to support 300 newtons of force. If you pull with more than 300 newtons of tension, that rope's most likely going to snap. So the rope can hold up 300 newtons of force. But wait just a moment. I lost my place. Okay, he weighs 500 newtons. But he's not falling. The rope is not breaking. He weighs 500, but the rope is only rated for 300. Why is the rope not breaking? Because
there's the rope on both sides.
Yeah, which is, I don't know about you, that hurts my brain. There's one rope, and that one rope is going over a pulley, so it can go either way. Yet, there is only half of the weight on each side. What? Yeah. This rope currently, now, let's look at reality here. This is a 1 kilogram mass. If I release, if I can do this without dropping everything, if I unhook this, all right. Now, you can't read the numbers on here, but this spring scale, see the little plunger here? It points at the reading on the scale here, and the scale says right now 1,000 grams, otherwise known as 1,000 grams would be 1 kilogram. And if you rotate it around to the other side, you see that it also is calibrated to read about 10 newtons on the other side. Okay, notice that if I release a lot of pressure, you see it go up and down like that, all right? So it's weighing both the weight and the mass of this 1 kilogram object. Now this, again, troubles me. It hurts my brain. There are many things, and remember, in physics, do not rely on common sense, because common sense will frequently fail you. This is like magic. Physics magic. If I take the other end of the string and attach it to Harry, and then release it like that, look what the plunger does. Okay, my knot just, what happened? I missed. Okay, try it again. Now look what happens. There we go. All of a sudden, it no longer reads 10 newtons. It's now reading 5 newtons. Half the weight. The moment I simply tie the string to the bosun's chair, the tension in the string goes down to half what it was before, which is troubling to the brain, but true. I mean, we can see it right there. You can see how much higher the plunger, even you can't see the numbers, but you can see the plunger is much higher than it was before. If I release the string, watch the plunger. I release the string. I think I release it. And look what happens to the weight. The plunger goes all the way down to 10 newtons again. 10 newtons, and then 5 newtons. Pretty cool. So Harry gets this brilliant idea. He's safe. This thing will hold 300 newtons, and he weighs 500. So how much tension is in the string? Only 250. Yeah, because he weighs 500. Yeah, 250. 250 on this side, 250 on this side. But it's the same string. I know, that's what hurts the brain. But it's 250 on each side. Total is 500. How can that be? Well, look at it. Behold. Here's the proof right there. It works. So then he gets this brilliant idea. Why am I tying this thing to myself? How about if instead I release the string, and instead I'm going to tie it to the flagpole over here. I don't have a flagpole. I could try to tie it way up there, but that's too far away. Maybe I can tie it to this flagpole. That flagpole's not going to work for me. Let's just tie it to this flagpole right here. Okay, there. Well, now all of a sudden, all of his weight is concentrated in just one rope. So now the rope is supporting all
His weight.
500 newtons, his entire weight, but the rope's only rated for 300 newtons, so as it says, he takes an early vacation in the hospital. String breaks. Fascinating. It still fascinates me. It all depends on where you tie the rope. Tie it to the flagpole, you're in trouble. Tie it to your own chair, and once again, you can do it again because I like it. Once again, tie it to your own chair and watch that plunger go from 10 newtons down to 5 newtons. Fascinating. I am supporting, think about this. Just think, if you think about it too much, there's a possibility that you might overload your brain. You could have smoke starting to come out of your ears. It can be dangerous. But I am now supporting 10 newtons of weight, and the scale says only 5. Because the scale is reading only one side of the string. It's actually 5 plus 5 for a total of 10. Weird. Now maybe for some of you, you're sitting there, well, it makes perfectly good sense to me. Okay. Yeah, it makes sense, but still. It's like physical magic. It's cool. All right, moving on. moving on from Harry the Painter and flipping the page to number 29. As you stand on the floor, okay? Yes, I am doing that as we speak. As you stand on the floor, does the floor exert an upward force against your feet?
Yes.
Yeah, not a trick question. Yeah, it does. Okay. And sometimes something is so simple and so obvious, you think it's got to be a trick question. Now, yeah, the floor does apply an upward force against my feet. How much force does it exert? A force equal to
Your weight.
my weight. Why are you not moved upward by that upward force? I mean, it's pushing up on me with about 150 pounds of force straight up. Why am I not flying up? Because it's being balanced by
Gravity?
my weight down, yes. I've got the support force of 150 up, being totally canceled out by my weight of 150 down. By the way, do you think that cancellation is perfect? Am I going anywhere?
No.
No. Is the cancellation perfect?
Yes.
Yeah.
Yep. Yep. My weight exactly balanced by the support force. How does it know to do that? That's all that stuff about the molecules of the floor being, held together with electrical bonds that are like little springs. And the harder you push the springs, the harder they push back, and it all comes out equal. It's bizarre. Isn't it cool how the world works? If only Aristotle had understood. Number 31. Can you say, yes, I can say anything I want. Can you say that no force acts on a body at rest?
No.
Yeah, this body here, what you guys see up there, that body there is at rest. Therefore, obviously then there are no forces acting on it. Wrong. Again, at least how many forces? 2. That's possessive form of the word it. It's weight. It's weight. And the other force? The support force. 2 forces at least. 2 forces. Could be more, but at least 2 forces. What was I forgot what the question was already. Can you say that no force acts on it? No, you can't say that. If a body is at rest, could there be no forces acting on it? What if it's flying through? What if it's at rest in space? Just sitting there, going nowhere, between Mars and Jupiter or something. Any forces acting on it?
No.
No. Well, Mr. Bear, gravity is anywhere. Okay, you're overthinking it. Yeah, if it could be that there are no forces acting on it. Or it could be that there are 2 forces acting on it. Or it could be that there might be 2, 4. Hey, I could do it wrong. Do this. There could be 1, 2, 3, 4, 5. All canceling. All we know for sure is that the force is canceled to 0, but I know there are at least 2 forces. Weight and support force. And I know they add up to 0. So just because something is sitting still does not mean that there are no forces. There could be no forces. If it's sitting still on the table, we know that there are definitely at least 2 forces. Now, what if, I'm not sure, I think he asked this, but I'm just jumping ahead a bit. What if I push it at a constant speed in a straight line? Now, at least how many forces? Well, there's still weight, that's 1. It's not falling through the table, so there's support force, that's 2. You're pushing it, that's 3. Is there another one? You can hear it, friction. So if I'm pushing it across the table in a straight line at a constant speed, there are at least 4 forces. What if it's just moving No one tells me if it's on the table, if it's in space, no one tells me anything. And someone says, hey, I've got an object and it's moving in a straight line at a constant speed. Do we have any idea how many forces are acting on it?
2.
Do we know that for sure? Maybe it's in space and there are no forces acting on it. Like an asteroid just shooting through space, no forces. Maybe there's no forces. Maybe there are 2 forces, like this. Constant speed. Maybe there are 4 forces. Do we know how many forces? No. If all you know is that it's moving in a straight line at a constant speed, and that's all you know, and you don't know where it is, you don't know what's going on, there's one number of forces it cannot be. If it's going in a straight line at a constant speed, there is one and only one number of forces it cannot be. 1. Because if there's only one force, it's got to remain unbalanced, and it's not going to be going in a straight line at a constant speed. It's going to be accelerating. A topic for chapter 3. All right, let's move on. Number 33, I think that's where we are. Okay, pull horizontally on a crate with a force of 200 newtons. That's not a lot of force. Pull horizontally on a crate with a force of 200 newtons, and it slides across the floor in dynamic. Ooh, don't let that word dynamic bother you. Dynamic equilibrium is just talking about the equilibrium of something that is moving. Dynamic referring to movement. He threw that word in there without defining it. Don't worry about it. It's the same thing as mechanical equilibrium. So we got this thing. I'm pulling on it with 200 newtons force. It is in equilibrium. How much friction is acting on the crate in the other direction?
200 newtons.
200 newtons. Because again, if it's sliding in a straight line at a constant speed, the sum of the forces must be
equal.
The sum of the forces must be 0. Therefore, the forces must be equal and opposite. If I'm pulling with 200, there's got to be something pulling the other way. And in this case, that would be friction the other way. Remember, friction always opposes motion. If the motion is this way, friction must be the other way. How do the magnitudes of weight and... Wait, I'm wrong problem. Okay, number 34. 34. 2 forces act on a parachutist falling in air. Weight and air drag. If the fall is steady, with no gain or loss of speed, then the parachutist is in dynamic equilibrium. How do the magnitudes of weight and air drag compare? Whether we like it or not, whether we believe it or not, those 2 forces have to be equal and opposite. They've got to be equal. If you're falling at a constant speed, then the downward force of your weight must be equal to the upward force of air friction. I have experienced that. Anyone ever skydived? No. I doubt it. Okay, my daughter did once. She did one of those things where they take you up a plane and they strap you on to some other dude who knows what he's doing, and they jump out of the plane together. I think she screamed all the way down. But I'm not doing that. But I have been to iFly. Yeah, it was cool. I'm glad we got some spare time. I'll tell you about iFly. If I thought about it in advance, I would have brought my computer tonight because I've got video of it. But if you ever get a chance, the problem with iFly is it's rather expensive. But I and my son went on a day when they had a free open house for educators. Because they want you to go as a teacher, they want you to love it enough to have your whole class come for a field trip. And they make lots of money. So it was a ploy to try to get you to bring your class. So they let us come free. And it's pretty cool. You've seen the building. You go down 270 and you see that weird, tall, rectangular building that says, iFly, indoor skydiving. What is that? It's basically a big wind tunnel. They got this crazy building, and someplace inside this building there is a fan. I think the fans are, I don't even know if they're at the top or the bottom. I have no idea if they're, I used to know. But you got a fan in some places, big old fans like this, you know, turning and blowing air upward. There's a kind of like a chain link fence here that you walk on here, and the air goes through it, and you can walk on this thing. And the air goes up to the top of this thing and goes through this this grate thing that's designed to keep you from flying through it. It would be very bad if you got sucked into the fan. And the air goes up here, goes around here, and goes back through. And what they do, they give you this suit and a helmet. The suit is kind of funny because you wear the special thing that covers your whole body, and it's got handles on it. There's a handle on the back someplace, and a couple of, maybe a handle on your legs. Or there are a couple of handles on this thing, so that the instructor can hold on to you, so that you don't die or something. So the time comes. It's your turn. The scariest moment is just before it's your turn. When you're sitting there waiting, do I really want to do this? And the instructor grabs you, and he steps into the thing and pulls you in there with him and makes you kind of lay down. As soon as you lay down, they turn up the speed on the fan there, and you find yourself just kind of like floating on this beautiful cushion of air. And all of a sudden, all fear is gone. As you're just laying there with your arms spread out and your legs spread out, and you're just kind of floating. They give you some instruction before you go in. They take you into a room and they teach you things like you want to keep your legs kind of stretched out. You don't want to curl them up like this. And they tell you that if you want to turn that way, you turn your hands like this. And the air will push you around this way. Then you can make yourself stop turning and then go the other way. And so you can change your direction by tilting your hands. And you can make yourself go forward or backward by how you tilt your legs. So they teach you these things. And so you got this instructor who's standing on the grate, and he's holding on to your handles while you're out flat like this, floating on air. Now, first of all, the funny thing about it is, which is kind of hard to comprehend, if I weigh 150 pounds, and I'm just floating here, in midair, just hanging there, and the guy is holding on to me just to make sure I don't drift in the wrong direction. He's holding on to my handles. But he's not supporting my weight. He's just keeping me under control as I'm laying here like this. If I weigh 150 downward, then the air friction on my body upward must be 150 pounds. Can air alone provide 150 pounds of upward force, of upward friction? Yes, if it's moving fast enough. It takes about 120 miles an hour of wind to give you enough friction to support your weight. The human body requires about 150 pounds of upward air speed to provide enough friction to hold you up. And it's cool because there's a glass, round glass wall all around you. And through the glass on one side, you see the control room. And they've got a computer screen set up there where you can actually see the wind speed. I was too occupied, maybe to some degree terrified, to bother reading what the screen said. But you can see your airspeed on the monitor there. And it's pretty cool. Then once the instructor feels like you've got a pretty good handle on what you're doing, he lets go of your handles and lets you fly all by yourself. And you're just kind of hanging there in the air. Indoor skydiving. And then they have you tilt your hands to turn. And then the other way. And then move forward and backwards. And if you manage to do all those things, then you get a certificate at the end with these things checked off. Right turn, check. Left turn, check. Move forward, check. And you get the certificate. So you did all these things. You win. Pretty cool. But you know how long it costs if you have to pay for it? It costs something like $35 or something. And you know how much time you get in there? 60 seconds.
Oh my God.
Which feels like a long time. It really does. 60 seconds is all you get. And there's a clock there on the monitor that counts it down. And when it gets down to the last 10 seconds, this red light starts flashing to tell you it's about over. And then right at the last moment, the guy just kind of grabs you and pushes you out the door. It's pretty cool. While we were there, they did it with a little kid. Little kid. It was hilarious. The guy has this little kid in there, and that kid grabs hold of the instructor's neck and will not let go. But his face, the whole time he's like, he was having a blast, but he would not let go. But then they let you do it twice. And the second time, they ask you if you want to go up. And you say, yeah, I'll go up. So you're in there, you're floating, and then they turn the fan speed up, and then the instructor stops standing. The instructor goes horizontal with you, and you both go up toward the ceiling. Up how many feet, I do not know. You know how tall that building is. He takes you way up, and then he has you kind of go in circles up there. And then they bring you back down. And then you go back up again, and you kind of go, this is so cool, I'm flying. It's neat. You ought to try it. $35 for 2 60-second sessions. It's worth it, I think. Once. I don't think I'd pay for it again. There are folks who pay for that over and over and over again and take lessons and get very good at it. The instructor then gave us a demonstration, which I have on video. He does the most bizarre things. He kind of goes in circles around the thing and like walks on the wall, and then he flies all the way to the top where you can't even see him anymore. Like, where in the world did he go? Did he go through that louver up there? And then he stays on the road, then he comes back down and he flies down, almost hits the floor, and then does this like Superman all over the place. He's doing flips and everything else. Really cool. They get very good at it. When he exited, his exit was dramatic. He goes all the way to the top, and he flies down really fast and goes right through the door and stands there. Like, good grief. So anyway, it was kind of cool. But the whole point of the story is air friction increases with speed. That's going to become an important concept in a later chapter. The air friction increases with speed. When you jump out of an airplane, well, not that you're going to, but if you were to jump out of a plane, the moment you step out of the plane, your speed is initially 0. But then you start to fall. Yeah, it happens. You start to fall. You accelerate faster and faster. The faster you go, the more air friction there is. When your body finally gets up to about 120 miles an hour, at that time, there's enough air friction on you that the upward air friction equals your weight. The moment the upward air friction equals your weight, at that moment, the net force on you is 0. So if the net force on you is now 0, does that mean you stop moving? Don't think I fly, think plane. You've just jumped out of a real plane. You're moving so fast, it takes about 120 miles an hour. You're moving so fast that the upward air friction equals your weight. What does your body then do? It simply keeps moving at a constant speed. You continue down at 120 miles an hour. You are in what's called terminal velocity. Terminal meaning, well, it kind of sounds when you hit the ground, it's terminal, but not that kind of terminal. Terminal meaning the final velocity, your last velocity. You're at 120. You're going to stay at 120 all the way down unless you open your parachute. Well, I should say not unless. How about until you open the parachute? Terminal velocity. So it's again an example of equilibrium. Sum of the forces being 0. Net force being 0. Because your weight downward actually equals the upward force of air friction. Pretty cool concept. Then what happens? You open your parachute, hopefully. Boom. All of a sudden, you got this big thing over your head that's catching a whole lot of air. Dramatically increasing the upward air friction. Because you got a whole bunch of upward air friction now, it's going to make you very suddenly do what? Yeah, slow down. You're going to slow down from 120 down to maybe about 20 miles an hour. But now, once again, with all that friction above you, once you slow down so that the upward air friction once again equals your 150 pounds of weight, you then continue down at a constant, nice, slow speed. More about that in a future chapter. But I thought I would just throw all that in because we have some extra time and because it's related to number whatever that was, number 34, the two forces that act on a parachutist. By the way, as you go down like that, you can control your speed. If you turn your body like this, then the air is not hitting as much of your body. You do this, now the air is only hitting your head and shoulders. Therefore, there's much less air friction. Therefore, your speed increases dramatically, and you get up to about 180 miles an hour before there's enough air friction to equal your weight. So you can go from 120 miles an hour to about 180 miles an hour by pointing downward. Then you want to slow down, you do this with your body, and you go back to about 120. So you can actually control your speed between 120 and straight down 180. And if you're good, like our instructor was, you can also change your direction flying like Superman. You know how to twist your body and move your hands. You can fly all over the place. Pretty cool. Well, I want to skydive. Well, try iFly first. Then decide if you want to skydive. Okay, let's take a look at 38. Last problem on the assignment. You toss a coin straight upward while riding a train. Where does the coin land when the motion of the train is uniform along a straight line path? Okay, so we're going along in the train. You're doing maybe 80 miles an hour going down this track. And you got a coin. Here's a weird, very strange looking coin. You've got a coin. There's the coin. Okay. Man, the screen went dark. I think that's just because maybe my battery's dying. The screen's really dark. Hey, if the battery dies, my apologies. Goodbye. But right, it won't come back. It's dark and it's like staying dark. I don't know what that
It
means for
probably
the
went
video.
on like low battery mode.
Yeah, and it's the video itself is probably okay. All right, so if I'm going along the train, constant speed, maybe 80 miles an hour.